doing?
Hey, I'm doing a falling rod lab, and we're finding angular velocity, angular acceleration, and angular position.
That's amazing. I totally love physics. So, how are you gonna do this? You've got a lot of things here.
Yeah, so the rod is 1.25 meters long, and we're dropping at an angle of
Yes.
66 degrees. And we're going to use veneer video analysis to capture its fall.
Okay, wait. So, you're doing, wait, you say 66?
66.
Why is 60 here?
Well, that changes the angle, adds an extra 6 degrees.
Physics wizards.
Hello, this is Osman. I'm going to talk about the relationship between angular position and time, specifically how we can get a time for the rod to fall with a given initial angular position. So to start the derivation, we can look at the conservation of energy, which gives us the final angular velocity in terms of gravity, theta, and length, which are all the variables we know. And to go further, we can look at the formula of angular position, which is 1/2 AD squared plus initial velocity times time plus initial angular position. And notice here the initial angular velocity is 0, so we can ignore that. And we just move the initial angular position to the left, which gave us delta theta equals 1/2 AD squared. And here we can also substitute our angular acceleration with changing velocity over changing time. And that gave us the time for the rod to fall in terms of theta, gravity, and length. And here, I just want to talk about how we get the angular acceleration and why that is a little bit inaccurate. So if we look at the angular velocity graph, it shows that the way we get our average angular acceleration is just to take the final angular velocity minus initial angular velocity and divide that with the time. And that's actually a little bit lower than what we would actually get, because if you look at the curve here, if we were to get the more accurate average angular acceleration, it would actually be a little bit higher. So yeah, and if we just plug in the number, the angular position, here we have 66 degrees, which is around 1.158 radians in length, to the equation we developed earlier, we can get a time for the rod to fall with 66 degrees is 0.4987 seconds. So here we can look at the angular position versus time graph. By looking at it, we found that radians, which is our angle, is getting smaller and smaller over time. It makes sense because as the rod falls, the angle between the rod and the floor becomes smaller. And besides that, we can also notice how the curve is become more steeper and steeper. That's because the gravity and also our angular velocity is become more negative as time goes on. And here is our multiple trials and percentage error. We find that out of our percentage error is below 30%, and we assume that the possible source of error could be air resistance. And I think what matters the most is the way we get our average angular acceleration, because we only take the finals minus initial angular velocity, which makes it a little bit imprecise. Also in the future, I think if we take more data points, it could make the result more accurate. Thank you.
Okay, for the theoretical final velocity at the tip, I had two ways that I thought of for solving for this. One is by using the components of the velocity vector in Vernier, as it gives an x velocity and a y velocity, and adding those components to give a velocity vector, a total velocity vector. And the other way was using the equation v equals omega r and solving for velocity that way. And that gave an a theoretical value of negative 5.79 meters per second. I wasn't able to get a theoretical value using the other equation because I didn't have any formulas for x component of velocity or y component of velocity, but using Vernier, I was able to get experimental values for that. Okay, so in Vernier, I set up the experiment by placing the plane like this. I sort of tilted the axes because it looks like the camera was tilted a little bit while recording, and the rod was sort of flat at this angle, and I just recorded points at the end of the tip of the rod, and it produced a graph of this when plotting the velocity versus the angle. Now, for the first velocity equation, what I did was I first had to make a speed equation by creating a calculated column that was the square root of the y velocity squared plus the x velocity squared. And then what I did from there was I created another calculated column, because the velocity would technically be negative since the rod is moving downwards and to the right. So I just created a calculated column that took the speed and multiplied it by a -1 to make a negative. And then for the other velocity equation, I took a calculated column from the theta velocity, which would be the angular velocity, and I multiplied it by 1.25, which was the length of the rod. And as you can see, both of the equations gave very similar values when plotted against theta. So it kind of validates each other that one of them is correct, or maybe they're both just slightly off from what the actual velocity is. And as you can see from the graph, the magnitude of the velocity decreases, but technically the velocity increases because it's becoming less negative as theta increases. And then when plotted against time, the final velocity was about -5.47 according to VTIP1, which was the component method. The components of the vectors for velocity method. And according to VTIP2, which was the L times omega method, I got about -5.46 meters per second. So both of these values are very close to each other, which again makes sense because they're solving for the same thing. And the theoretical velocity was about -5.79 when using the omega times the radius method. And that was a little bit higher than both what VTIP2 and VTIP1 got during the experimental trials. which makes sense because neither, well, not neither, but this equation v equals omega r doesn't really take into account maybe like misclicking at the tip of the rod, and there could be errors from forces applied by air resistance in the opposite direction of the rod's movement, and by friction at the hinge of the rod, like inside here, as the rod falls.
So first, we're going to look at angular velocity versus theta. I developed this graph using Vernier video analysis. As the rod fell, I tracked its position, and then I graphed angular velocity against theta. And as you can see, as theta increases, the magnitude of the angular velocity decreases, and it seems to be at a slightly increasing rate, although some portions of the function seem linear as well. So that's the relationship between angular velocity and theta right there. So moving on, I'm gonna take you through the derivation for the final angular velocity. And so to do this, I used an energy approach, and the rod's final kinetic energy can be considered equal to its initial potential energy, and that leads to this right here. mgh is 1/2 I angular velocity squared. And when we plug in and rearrange, you get this expression is equal to the angular velocity. Well, then we can plug in some known values. Gravity as 9.81, 66 degrees as the angle it was dropping, and we measured a 1.25 meter length for the rod, and plugging in those known values, get an expected angular velocity of 4.64 radians per second. Experimentally, I used Vernier once again to get a value for angular velocity, and I just graphed angular velocity against time. And the final point on that graph should be what the angular velocity is, and that's a magnitude of 4.21 radians per second. And then that same method was repeated a couple of times to develop the angular velocity for 3 more trials. And the average angular velocity is 4.46 radians per second, and that was determined experimentally. So comparing the experimental angular velocity to the theoretical, you can see that the theoretical is actually greater, and there's a 4% difference in the theoretical and the experimental angular velocity. And that could be due to air resistance, and that would explain why the theoretical angular velocity is greater, because it doesn't account for the air resistance, which slows the velocity down, as well as human error in plotting the points, or the fact that the frame rate was only 60 frames per second could be greater, and then maybe the Vernier derivation, I tracked position, and I'm graphing velocity here, so maybe there's some discrepancy there, and all those factors probably contribute to that 4% error.
So for theoretical angular acceleration, I knew that angular acceleration of an object was directly proportional to the net torque acting on it. So I used the following equations for torque and angular acceleration to solve for a theoretical value of angular acceleration, and then I plugged in the known values of 66 degrees that the rod fell at, and then its length of 1.25 meters to find a theoretical value of 4.788 radians per second squared for the initial angular acceleration. So, to find the experimental angular acceleration, I used Vernier video analysis to plot the angular velocity versus time, and then I found that a quadratic curve fit applied to this graph. So then I took the equation of the quadratic curve fit and then substituted 0 for time because I was solving for the initial angular acceleration, and I got an experimental value of 4.737 meters per second squared. That's the magnitude of the angular acceleration. So in order to calculate the percent error, I took the value that I got, the experimental value that I got minus the value that I expected, and then I divided that by the value I expected, and then I had a 1.06% error. And potential sources of error include air resistance and maybe even incorrect measurements of angle or the length of the rod. And then finally, I graphed angular acceleration versus angle. And to do this, I created a calculated column in Vernier, which was just the first derivative of angular velocity with respect to time. And then I noticed that there wasn't really an apparent trend between angular acceleration and versus angle. but this is probably because Vernier software has difficulty in analyzing non-constant accelerations, which means when there's jerk present. So that was probably the reason for just an inconsistent trend of data. And that is all.